Hello students, welcome to Inside Physics. Today we are going to discuss about a concept in simple harmonic motion. See, where we have considered a particle in uniform circular motion. Okay, see, the projection of the particle in uniform circular motion on two diameters is also making simple harmonic motion. That is what we have to prove here. So, the concept is simple harmonic motion in uniform circular motion. So, why we have to consider uniform circular motion and why we need to draw a projection from the particle which is moving in anti-clockwise in circular motion with a uniform angular velocity. So, this P is the particle which is moving in uniform circular motion in anti-clockwise with angular velocity omega, and this n is the foot of the perpendicular drawn to this diameter y dash. This is another diameter xo x dash. So these are the two mutually perpendicular diameters in this circle. So here our aim is to prove the projection, that means the foot of the perpendicular M drawn from P. This is the projection from P to this diameter. Pn is another projection onto the diameter y dash. Y dash. Okay. So our aim is to prove the projection is making simple harmonic motion while the particle is revolving in the uniform circular motion in anti-clockwise with uniform angular velocity omega. When we can say a particle is executing uniform circular motion? If it is moving with uniform angular velocity, uniform angular velocity. So it is represented with omega. Then we can say a particle is moving with uniform circular motion. So how to prove the projection? Suppose in this case we consider the projection Pm. While the particle is moving in circular motion, this projection will also make oscillations on the diameter xo x dash. Now we will prove the projection, the motion of projection on this diameter is simple harmonic. That is our aim. So how to prove it? First of all, if any motion needs to be simple harmonic, that must be periodic, right? That must be periodic first of all, and it should oscillate about a mean position. These are the conditions which we already discussed in the previous classes, the conditions of SHM. Okay, and the acceleration must be always directed towards this mean position, and acceleration of this projection which we need to prove is directly proportional to displacement, and it is always directed opposite to the displacement. Okay, what is the displacement here? Displacement of the projection from mean position. If we consider this as mean position for the oscillation of projection, this is the mean position, and the displacement is nothing but displacement is the path length from mean position to the extreme position. Okay, so here we'll go into the details how we can prove the projection is making a simple harmonic motion. Okay, we know that the particle is moving in anti-clockwise with angular velocity omega. Okay, See, then the time period for the particle to complete one revolution is time period is equal to 2 pi by omega, right? The time period for this particle to move complete one circular motion is nothing but 2 pi by omega, where omega is the angular velocity. Okay, here the theta is angular displacement, right? The theta is angular displacement. This is written as omega t plus phi. So what is phi? While the particle is moving in circular motion anticlockwise, the time at time t is equal to 0, the position vector of particle, that means PO, the position vector of particle is making an angle phi with the horizontal. Remember, at time t is equal to 0 means we are considering the particle has just started or it is already in motion, whatever it may be. We consider the initial time t as 0. At that junction, the position vector of P is making an angle phi with the horizontal. So here the angular displacement is phi. Okay, theta is equal to phi. After some time, where t you can say is equal to t, after some time t, the angular displacement will be omega t plus phi. Why means, see, in time t it has moved an angular displacement of omega t. In a time span of t 0 to t, the particle has moved in an angular displacement of omega t. Why? Because omega is angular velocity, time is the time interval. So omega t plus phi, from 0 to t, the total angular displacement is omega t plus phi. So here, if t is the time period of one revolution for the particle, then we can easily say, see, the projection Pm is also making one oscillation in the same time period. Okay, in the same time period, the projection Pm is also making one oscillation. So the time period of one oscillation of the projection is also t. Okay, so now we move to how the next acceleration is considered here. Before that, with this assumption, we know now we can say the projection Pm is having periodic motion, having periodic motion. So the time period of one oscillation is this one. So projection Pm is having periodic motion, right? So first condition is satisfied for SHM. The next one, acceleration. How the acceleration is considered for this projection. Here, if you can observe the angular displacement, what I have written is theta is equal to omega t plus phi. And what is cos theta here? If you observe POM is the triangle, then cos theta is adjacent side by hypotenuse. So we can write cos theta is equal to OM by OP. OM by OP. So what is OM here? Adjacent side, nothing but displacement, right? X by OP. This is nothing but radius, right? Radius, and we can mention it as A, radius of the circle. So OP by A, right? So what is displacement here? X is equal to A cos theta. So A cos, what is theta here? Omega t plus phi. Omega t plus phi. This is the displacement of this projection. That means from mean position to the extreme position. So this is the displacement. Okay. So now, what is the centripetal acceleration of the particle P? We know that for any particle which is having a circular motion or rotatory motion, it must be having a centripetal acceleration which is always directed towards the center of the circle. So, what is the acceleration here? Centripetal acceleration of the particle we can write a omega square, right? A omega square, that is the centripetal acceleration. Now, here this is the particle acceleration, centripetal acceleration of the particle, and here we want the acceleration of projection pm, acceleration of this projection. That's what we want to prove, right? The acceleration of projection must be directly proportional to the displacement and must be directed towards the mean position and exactly opposite to the direction of displacement. That's what, if you can, we can prove that, we can say the projection is making an SHM. Okay, the projection is of the particle. Now, what is the acceleration of the projection? AM. How can we get it? AM, acceleration of the projection. So if this is the centripetal acceleration directed towards this point, we can have this made into two components. So this component, this is Pn, projection of Pn. The acceleration of Pn can be written as a omega square sine theta, and the acceleration of projection Pm can be written as a omega square cos theta. So see, here the centripetal acceleration of the particle is directed towards the center of the circle, and the centripetal acceleration is divided into two components. Okay. So along this direction, the centripetal acceleration of the projection Pm can be considered as a omega square cos theta. A omega square cos theta. We know theta is equal to omega t plus phi. So we can write a omega square cos plus phi. Okay. If you observe this one, x is nothing but a cos omega t plus phi. Okay. And am, acceleration of the projection, is a omega square cos omega t plus phi. So with this we can write am is equal to, see, this can be written as x. I will write it as omega square x, acceleration. So x is nothing but this value, a cos omega t plus phi has become x. Why I have put minus here? The negative sign means the acceleration of the projection is always directed towards mean position, and the displacement is always directed from mean position to this side. So both are in opposite direction. That's why to indicate the direction of acceleration and displacement, I have put the negative sign before this one. So here omega is constant, right? Angular velocity omega is equal to constant. If omega is equal to constant, what we can write? Acceleration am directly proportional to minus x, right? Acceleration of the projection directly proportional to displacement, and it is in the opposite direction of the displacement. Okay, that is exactly nothing but the condition of simple harmonic motion. Okay, so in this way, what we have done, first we proved that the projection Pm from the particle which is moving in a uniform circular motion is periodic. First we proved, and the time period of the projection is t is equal to pi by omega. After that, the second condition, which is an actual definition of SHM, so the acceleration of projection must be directed towards a mean position, and it must be directly proportional to the displacement, and it should be in the opposite direction of the displacement. So everything is satisfied here regarding the simple harmonic motion. So with this we can say that the projection of a particle in uniform circular motion is having simple harmonic motion. Okay, now we can prove this with the projection Pn also using the same theory, and the acceleration of the projection Pn is a omega square sine theta. Okay, here we have taken two projections, one onto the diameter y o y dash, one onto the x o x dash. We have taken the projection Pm and proved that the oscillations of projection Pm are nothing but are making simple harmonic motion. So this is how we proved in this way, and in the next classes we will see some more topics of simple harmonic motion. Okay, thank you.